Hey everyone, this is Gal speaking. A quick introduction of myself. I'm currently the CTO and co-founder of Intsights. The following presentation will introduce you to how Insights solved its scale problems and why we switched from Celery to a homegrown solution. In the presentation, we will talk about why we initially chose Celery and what were the reasons we switched to our solution. We will also talk about what's behind the distributed task queue mechanism. Let's dive in. As for the agenda of this session, we'll briefly talk about the problem, why we decided to build a Celery alternative. We'll talk about some of Sargent's architectural decisions and compare and demonstrate Sargent versus Celery. So back in the days, about 6 years ago, we were a young startup and had big dreams. We won't get into details about Insights' core business, but we had a technological challenge: scraping billions of pages a day quickly and efficiently, all in Python. As the company grew, the demand for more and more resources increased. This is when we started tackling more and more production problems. So it starts with the tremendous load on our RabbitMQ servers. We've seen them going down more frequently, and we had to spin up more and more servers to handle our increasing load. Eventually, we decided to switch to Redis as we've seen better performance and we didn't care about tasks being dropped. Redis performance was much better, but our workers again hit a point where they couldn't handle the load, and our Redis clusters were permanently exhausted. This was only the beginning, of course. As we implemented more and more workers and logic to analyze the scrape data, transform it, and do more tasks, we started seeing problematic behavior derived from Celery's concurrency model and process safety. It began with hanging workers that became randomly stale. It followed with timeouts that weren't respected or resulted in considerable delays. While attempting to solve all of these problems, we came to the evident conclusion that we must have full control over our infrastructure if we were to succeed. This is where Sargent was actually born. First, I'd like to add a note: Celery is not bad. It's actually pretty great. It is a mature library with huge community adoption. It has tons of miles of experience and many users. The problem was that Celery did not satisfy our needs. So the real topic is actually what is wrong with Celery for our use case, specific use case. So let's start with the use case. So our use case was producing and consuming billions of relatively short tasks a minute. And Celery is highly optimized for RabbitMQ. We won't get into details about what is MQP, but we didn't want the overhead of this protocol. Celery guaranteed the task will not fall through the cracks. Um, so when a worker pulls a task, it is guaranteed to be handled, or the task will become accessible for other workers to consume. Celery's reliance on AMQP and task acknowledgement made it slower. Celery's Redis connector is implemented with acknowledgement emulation to be on par with the RabbitMQ implementation, and it made the Redis connector much slower. Another problem was with Celery's concurrency model. We won't get into details about this one too, but handling task execution is not as simple as it may seem. There are many edge cases, such as a task holding the GIL and will not get notifications from other threads that try to tell it that it has exceeded its configured delay. What if we were talking about an infinite task that will never allow other threads to stop it? So it ended up with thousands of stale workers in production. It actually happened. Celery's approach of pushing and pulling a task does not leverage batch operations, at least with the Redis connector. Not only that, but the Redis connector opens by default a new connection on each interaction with the broker. Think about pushing billions of tasks, and each push operation opens a new connection and closes it. This is a substantially redundant process. Celery has its metric mechanism. You can disable it, of course, but by default it is enabled, and it is leading to a significant overhead on the brokers. The biggest of problems was that we had no control over Celery. When we had a problem, even if we knew how to solve it, it took a lot of time to bring it to the upstream code. We needed much more control over our code. Let's move forward. Let's talk briefly about what is distributed task queue mechanism. I won't get into details about here, since this is not the scope of the presentation, and I assume most of you are familiar with this concept, but I still want to be sure we are aligned. So there are three main actors in this diagram. There is a producer, whose role is to produce tasks. These tasks are being pushed into a broker, whose position is to store and distribute the tasks. And the last part is the worker, also called consumer, whose role is to pull tasks from the broker and execute them. A worker can also act as a producer and push tasks into the broker on its own. In any case, this whole system exists in order to enable distributed compute resources to work separately. Let's take a look at a scraping task. We have a producer pushing a task with the main URL of some desired website. A free worker from the pool pulls this task and browses to the main URL. As part of its logic, it extracts the links from the HTML, and for each link, pushes a new task. Other free workers, potentially from different machines, pull additional tasks and execute on them. This process grows exponentially. This system ensures good distribution and resource utilization across different machines and multiple cores. Whenever a worker is free to work, it pulls another task and executes it. This is the mechanism in a nutshell. Here we have a table comparing metrics and features. The main thing here I'd like to emphasize is how much code Celery contains as opposed to Sargent. Celery is built out of 3 different libraries. We won't get into details here too, and the purpose of each of the libraries, but they are totally dependent on one another. So I decided to measure them all together. As you can see, Celery consists of more than 65,000 lines of code. Sargent, on the other hand, consists of only 4,000 lines of code. It does indicate some things that are important to note at this point. The first is that Sargent is far slimmer than Celery. It indicates that the library includes probably fewer features than Celery, which is right, by the way. That is easier to maintain because it's perhaps much less complex, and that's it. I don't think we can conclude anything else out of this table. I want to talk about 2 fundamental differences between Celery and Sargent's way of pushing and pulling tasks that tremendously impact the performance of high throughput workloads. Worker consuming many tasks a second and complete each of them in milliseconds will benefit from bulk pushing and pulling. Let's simulate. Think about a worker that does a very fast task, like parsing 1 kilobyte of HTML. This probably lasts for a few milliseconds. Now, if it will pull 1 task at a time from the broker, it will bother the broker tens or hundreds of times a second. Now, think about this problem in a magnitude of thousands. We want the worker to interact with the broker in a sweet spot where it does not bother it too much, yet not rarely interact with it. The first would result in too much congestion on the broker, and the latter would make task distribution uneven, where some workers would pull most of the tasks in cases where there are not enough tasks for the number of online workers. Back to the differences. Celery does not work in batches, nor provides a idiomatic way of doing so. Bear in mind that I'm comparing Celery connected to a Redis broker against Sargent connected to a Redis broker. It's probably a bit different when working with RabbitMQ, but we wanted to compare apples to apples, and we had no intention of moving back to RabbitMQ. Celery's way of pushing tasks work in the following manner. On each apply async invocation, a new Redis connection is opened, and a new task is pushed. Sargent, on the other hand, reuses the same connection for the whole worker lifecycle. Sargent also includes an API to push multiple tasks at once with a batch API. This function allows us to use Redis batch operations, which are much faster. The same goes for pulling tasks from the broker. Celery contains a parameter called worker prefetch multiplier, which controls how many tasks should be pulled from the broker at once. After we profiled the worker, tweaking this parameter did not change the behavior of our worker with Redis. Celery has just continued pulling tasks one by one. Sargent, on the other hand, leverages Redis batch API, which makes it significantly faster. Another thing that Celery does that impacts performance is simulating AMQP-like behavior with acknowledgements on top of Redis. I won't dig into that, but it definitely slows it down. Here you can see a chart comparing the time it takes to push a very small task in Celery compared to Sargent. Just to clarify, both were using Redis as a worker. You can find the benchmark examples on our GitHub repository under the benchmarks folder. I reused the same connection in Celery's example and didn't find it to increase the throughput too much. The Sargent's number refer to two different methods. The single method pushes tasks one by one, and the batch method pushes 25,000 of tasks at a time. You can see the performance gain from working with batches. This chart explains how important the performance improvement for huge workloads lies in the second chart. The time it takes to execute 100,000 tasks. If you have many tasks, each taking a millisecond to complete, you don't want to pay so much time just for the framework's overhead. You want your code to execute fast without delays. Working with longer tasks decreases the amount of drama here, because if each task takes more than a few milliseconds, paying 5 milliseconds would not be considered high cost. Let's move forward. Let's talk about some of the concepts we emphasize in Sargent to make it simple, highly performant, and safe. First, it is essential to define what we mean when we say safety and reliability. Let's talk about safety first. When you push a task to the queue and an arbitrary worker somewhere in your infrastructure pulls the task, you want to be sure that the task will be completed successfully. There are multiple endings for a task. The first, it will finish successfully. The second, it will raise an exception and will fail to complete successfully. These are the two common scenarios, but there are other more rare scenarios that we should consider and handle appropriately. What happens when a task is running for too long? Of course, we will set a timeout, and once the timeout arrives, we will stop the task while it is running. But wait, how do we stop an in-progress task? What does that even mean? So the experts here will probably say, hey, we can raise an exception from another thread. That's right. But wait, what happens if the in-progress task thread is holding the GIL? That exception would not be handled unless the worker will release the GIL. What if the task has called a library that overloads the signal handler that is taking part of the timeout mechanism? What happens if the task is holding the GIL and is stuck infinitely, for example, in an infinite regex? Assuming we solved all of these problems, how would we keep the worker performing correctly? Performing correctly and fast. Sargent's answer to all of these questions and issues lies in two mechanisms. The first is the killer. A killer is a device, an application device of course, responsible for telling the running worker, hey you are running for too long, you should stop because you exceeded your defined timeout. And if it does respond, kill it ungraciously. And if it does not respond, kill it ungraciously. This mechanism is tough to implement while keeping it both performant and reliable. For example, and without getting into too much detail, our process killer is a device that is implemented as a different sub-process that watchdogs the worker and send it signals. The device has an internal clock that counts the duration of the current task. The worker should communicate with the killer to tell it once it is finished to stop the killer before it sends a signal for no purpose. This IPC between the worker and its corresponding killer should happen fast. Sending this data back and forth hundreds of thousands of times can negatively impact performance. The second device we implemented to keep the framework safe and reliable is the supervisor. The supervisor is the process that spawns the workers and makes sure they run. It is also responsible for cleaning up after the worker exited, either gracefully or not. The cleanup part is essential and not trivial to understand. You might find yourself using sub-processes for different tasks in the world of Docker containers. and complex workloads. And killing a Linux process can end up leaving zombie processes. I won't get into much detail here too, but the supervisor is responsible for clearing these zombie processes and acting as a straightforward init script. Another thing that can cause workers to hang and to refuse to exit is non-demonic threads. As you might know, the Python interpreter does not allow the main thread to exit unless additional non-demonic threads, unless there are additional non-demonic threads. What happens if your program leaks such threads? I will tell you a secret. PyMongo uses some non-demonic threads that might get your interpreter stuck. This is the purpose of the supervisor. At first, our implementation was very simple and straightforward. Still, as we grew and tackled more and more production issues, we adapted fast and ended up with a very rigorous system. There are some reasons that the library is Swift. I talked about many of these aspects before, so that we'll talk through them briefly. The library leverages batch operations. It makes it rapid with tiny duration tasks. It also leverages the iRedis library, which shines with batch operations, and is also implemented in C. We implemented only 2 backends. This is the second point. We implemented only 2 backends, and we tailored them to our specific use cases. We did not try to support AMQP-like operations and task commitments. This trade-off should be considered while choosing this library, of course. The third point, every single line of code in the library has been profiled multiple times and optimized. Last, we switched the implementations to make the library fast and safer. We switched a lot of implementations during the development of the library to make it much faster and much safer. Timeouts are implemented in a very lightweight manner without compromising consistency and reliability. Lastly, as an added bonus, 2 Redis issues that we've pushed during our library. One of them during our library development. One of them has been merged lately, and the other is in the following minor backlog. The last thing we want to emphasize is simplicity. Scaling was at the core of this feature. We didn't want to handle the complexity of the clusters. First, they are hard to maintain. Second, migrations and sharding mechanisms become much more complex with large-scale deployments. We wanted to make the whole process as easy as possible. This is why we treat clusters as simply separated standalone instances. We handle the tasks distribution on the client side. It makes your deployment much easier, but compromises the tasks pushing and pulling ordering. The second part is that the library is fully type annotated. It helps you write code faster and with fewer bugs. The third point is that you can customize the worker in many different ways, and you can implement your internal mechanism quickly and safely. I will show an example in the next slide. The fourth point is that our workers are class-based. It makes the whole logic listed in one place and makes code organization much easier. You won't find yourself seeking configuration files and separated logic files. I want to show how a worker skeleton looks like with an APM, application performance monitoring, hooked in as part of the worker. The following example will emphasize the simplicity and elegance of using the library. So in front of you, you can see a very simple Sargent's worker code that overloads 4 functions to hook an APM solution to the worker. Number 1 is, of course, importing an example APM library. In that case, we use Elastic APM. Number 2 point is the Elastic APM client initialization. As you can see, it is defined in a function called initialize. This function gets called once for the whole worker lifecycle. This is where you should put code that defines state or initializes some connections. In that case, we set the Elastic APM client object creation. But if the worker was a real worker, you could have found there things like PyMongo client or some one-time calculation. Point number 3 marks a beginning of a transaction. Not by chance, the name of the hook is called pre-work. Pre-work is a function that is being called on each new task before its execution. It allows you to hook in actions that should happen before a task starts executing, such as resetting a state. Points number 4 and 5 marks the end of the transaction. In case of an exception, you can see that we make sure the APM knows it. The hook's name is post-work, and it is guaranteed that it will be called after each task's execution, regardless of the reason it finished. Either it finished successfully, raised an exception, etc., etc. Point number 6 exists in a function called finalize, which is being called once in a worker's lifecycle before it exits and being respawned by the supervisor. This is the place to put finalization code, like closing connection gracefully and clearing some mess. If you ignore our coding conventions, which do not save lines, you will see that the whole APM embedding took around 10 lines of code. Feel free to ask any questions in the platform. I'll be there to answer any questions. I would like to thank you for listening to this whole presentation and our journey. I hope you enjoyed it. I would like to thank PyCon for hosting our presentation. I would be thankful if you contributed to our library in GitHub under Intsights/Sargent. You have the URL in the current slide. Feel free to reach out and open issues. Bye bye, folks.